So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's light hitting your eyes. Not a lot of it, maybe just the soft glow of a screen or a lamp across the room, but it's there. And your eyes, these small, wet, imperfect little organs, are collecting that light, bending it, focusing it onto a patch of cells at the back of your head, and from that, your brain is constructing an entire world. Color, depth, motion, meaning, all from light. That's what a telescope does too. It just does it better. And the story of how we figured that out, how we went from squinting at the night sky with nothing but our bare eyes to building machines that can see galaxies 13 billion light years away. That story is one of the most human things I can think of. It's full of accidents, rivalries, obsessive geniuses, spectacular failures, and moments where someone looked through a tube of glass and saw something that changed everything we thought we knew about where we are in the universe. So, let's start there. Let's start with just your eyes and the night sky, and what people could figure out before telescopes even existed. Because honestly, it's remarkable how far they got. If you'd been born a few thousand years ago, say in ancient Mesopotamia or Egypt or Greece, the sky would have looked completely different to you. Not because the stars were different, but because you would have actually seen them. No light pollution, no city glow, no screens, just darkness, and above you, this overwhelming dome of stars, thousands of them. On a clear night, the human eye can see somewhere around 4,000 to 5,000 individual stars, and ancient people knew them intimately. They tracked them, named them, built entire cosmologies around their patterns. And here's what's impressive. Without any instruments at all, just careful observation over generations, ancient astronomers figured out a shocking amount. They mapped the motion of the planets, those wandering stars that didn't follow the same fixed patterns as the others. They predicted eclipses. The Greeks measured the tilt of the Earth's axis. Eratosthenes, around 240 BC, calculated the circumference of the Earth using shadows and geometry, and he got it right to within a few percent. That's with sticks and shadows and a really good brain. But there was a wall, a hard limit, and that limit was the human eye itself. Your pupil, when it's fully dilated in the dark, opens up to maybe 7 or 8 millimeters across. That's it. That's the biggest light-collecting aperture your body can give you. And that tiny opening determines everything. How much light you can gather, how faint an object you can see, how much detail you can resolve. For thousands of years, that was the boundary of human astronomy. Everything we knew about the universe had to pass through an opening smaller than a pencil eraser. Think about what that means. There are objects in the sky, nebulae, distant galaxies, faint stars, that are pouring light down on us all the time, but in quantities so small that 7 millimeters of pupil just can't collect enough of it for your brain to register. The information is right there, raining down on you, and you simply can't see it. It's like trying to fill a swimming pool with a thimble. The water exists, you're just not catching enough of it. So for a very long time, the universe appeared to be a certain size, with a certain number of things in it, and that appearance was entirely a function of our biology, not of reality. And nobody knew that. Nobody could know that. You can't miss what you've never seen. Now, to understand how telescopes broke through that wall, you need to understand a little bit about light itself, and specifically about what happens when light passes through glass. And this is one of those things that's so familiar to us now that we barely think about it, but it's genuinely strange and beautiful when you slow down and really look at it. Light travels in straight lines. You know this intuitively. Shadows have sharp edges. Sunbeams come through windows in neat shafts. But when light passes from one material into another, from air into glass, say, or from air into water, it bends. It changes direction. Not by a lot, usually, but it bends. This is called refraction, and people have known about it for a very long time. Anyone who's ever looked at a stick poking into a pond and noticed that it seems to kink at the water's surface has seen refraction in action. The reason it happens is that light travels at different speeds in different materials. In a vacuum, light moves at its maximum speed, about 186,000 miles per second, which is just an absurd number. In air, it's almost the same, just slightly slower. But in glass, light slows down noticeably. And when a wave, any wave, not just light, hits a boundary where its speed changes, it bends. There's a good analogy for this. Imagine you're pushing a shopping cart across a parking lot, rolling along on smooth asphalt, and then one wheel hits grass. That wheel slows down, but the other wheel is still on asphalt, still going fast. So the cart turns. It pivots toward the slow side. That's essentially what light does when it enters glass at an angle. One side of the wave front hits the glass first, slows down first, and the whole beam swings around. Now, ancient people knew about refraction in a general sense. The Roman philosopher Seneca wrote about how a glass globe filled with water could magnify things. The Arab scholar Ibn al-Haytham, and he's someone we should really talk about, wrote extensively about optics around the year 1021 in a work called The Book of Optics, or Kitab al-Manazir. Ibn al-Haytham was extraordinary. He was working in Cairo, and he essentially laid the foundations of modern optics. He understood that vision works because light enters the eye, not because the eye sends out some kind of beam, which was actually the competing theory at the time, going all the way back to Euclid and Ptolemy. The idea that your eyes emit rays that touch objects and bring back information. It sounds strange to us now, but it was a perfectly reasonable hypothesis for a long time, and Ibn al-Haytham was one of the people who killed it. He studied reflection, refraction, how light bends through curved surfaces, how lenses work. He described the camera obscura, that simple device where light passes through a tiny hole and projects an inverted image on the opposite wall. He was methodical, experimental, rigorous. Some historians call him the first true scientist, in the modern sense of someone who systematically tested hypotheses against observation, and his work eventually filtered into Europe, translated into Latin, where it influenced Roger Bacon, Kepler, and eventually the people who would build the first telescopes. But here's the thing. Even Ibn al-Haytham, brilliant as he was, didn't build a telescope. Neither did anyone else for another 500 years after his work. And the reason is interesting. It's not that people didn't understand lenses. By the late 1200s, Europeans were making spectacles, eyeglasses. We know this because there are paintings from the 1350s showing people wearing them, and written references go back even earlier to around 1286 in Italy. So the technology of grinding glass into curved shapes that could bend light in useful ways, that existed. People were walking around with lenses strapped to their faces. But it took another 300 years for someone to think of putting two lenses together in a tube and pointing the thing at the sky. Why? Why the gap? It's one of those questions in the history of technology that's genuinely puzzling. Part of the answer is that making good lenses is really hard. Early spectacle lenses were rough, full of bubbles and imperfections, and they were designed for a very specific, practical purpose, helping aging eyes focus on things up close, like text. The idea of using lenses to see things far away, to magnify distant objects, that's a conceptual leap that seems obvious in hindsight, but wasn't at all obvious at the time. People were thinking about lenses as medical devices, as aids for reading, not as instruments of discovery. And then, around 1608, something happened. Or rather, several things happened almost simultaneously, which is often how breakthroughs work. Not one lone genius in a tower, but multiple people converging on the same idea, because the underlying knowledge and technology have finally reached the right point. The story most people know starts with Hans Lippershey, a spectacle maker in Middelburg, in the Netherlands. In October of 1608, Lippershey applied for a patent on a device he called a kijker, a looker. It was a tube with a convex lens at one end and a concave lens at the other, and when you looked through it, distant objects appeared closer. About 3 times closer in that first version. Not a huge magnification, but enough to be remarkable. But here's where it gets messy, and honestly, kind of fun. Lippershey wasn't the only one. Within weeks of his patent application, another Dutch spectacle maker named Jacob Medius filed a similar claim. And there are references to a third person, Zacharias Janssen, also from Middelburg, also making similar devices around the same time. There were even rumors that Janssen's children later claimed their father had built one first, back in the 1590s. The historical record is tangled, and scholars have been arguing about it for centuries. What we do know is that Lippershey's patent application was denied, not because the device didn't work, but because the Dutch government decided the invention was too easy to copy and therefore couldn't be meaningfully patented, which is kind of hilarious and also kind of telling. The basic telescope was, in some sense, simple. 2 lenses, a tube. Once you knew it could be done, replicating it wasn't that hard, and word traveled fast. Within months, telescopes were being sold at fairs across Europe. They were novelties at first, curiosities. People used them to look at ships in harbors, to spot distant landmarks. Military applications were obvious. You could see an approaching army long before they could see you. But no one, in those first months, seems to have thought seriously about pointing one upward. No one, that is, until an Italian mathematician heard about the Dutch invention in the spring of 1609 and decided to build his own, and build a better one, and then do something with it that no human being had ever done before. His name was Galileo Galilei, and he was 45 years old, a professor at the University of Padua, perpetually short of money, supporting a family that included 2 daughters he'd placed in a convent because he couldn't afford their dowries. He was brilliant, argumentative, witty, and ambitious. And when he heard about the Dutch spyglass, he didn't just want one. He wanted to understand how it worked, improve it, and use it to advance his career. Within a single night, according to his own account, he worked out the optical principles. Within days, he'd ground his own lenses and built a telescope that magnified about 8 or 9 times, already nearly 3 times better than Lippershey's original. He presented it to the Venetian Senate, who were so impressed they doubled his salary. And then he kept going. By the end of 1609, he had a telescope that could magnify 20 times, and that winter, he turned it toward the sky. What he saw in those cold months at the end of 1609 and the beginning of 1610 changed the world. I mean that literally. The things Galileo observed through that crude, small, imperfect tube of glass dismantled a cosmology that had stood for nearly 2,000 years and set in motion a revolution in human understanding that we're still living inside of. He looked at the moon first, and instead of the perfect, smooth, crystalline sphere that Aristotelian philosophy demanded, this unblemished heavenly body fundamentally different from the corrupt, messy earth, he saw mountains. He saw craters. He saw shadows cast by peaks, and he used the geometry of those shadows to estimate the mountain's heights. The moon was a world, a rough, cratered, imperfect world, not so different from our own. And that was just the beginning, because what Galileo did next was even more extraordinary. He turned the telescope toward Jupiter, and on the 7th of January, 1610, he noticed 3 small stars near the planet that he hadn't seen before. They were arranged in a neat little line, and at first he thought nothing of it, just faint fixed stars that happened to be near Jupiter in the sky. But the next night, they'd moved, and the night after that, they'd moved again. Over the course of about a week, he watched these tiny points of light shift position relative to Jupiter, sometimes appearing on one side, sometimes on the other, occasionally vanishing entirely, which he eventually realized meant they were passing behind the planet or in front of it. By the end of January, he'd found a 4th one. And the conclusion was inescapable. These weren't fixed stars. They were moons. They were orbiting Jupiter. Now, think about what that means in the context of 1610. The entire argument against the Copernican model, the idea that Earth goes around the sun, one of the most powerful arguments against it was this: if the Earth moves, why doesn't the moon get left behind? How can the Earth be in motion and still drag the moon along with it? It seemed absurd. But here was Jupiter, clearly moving through the sky, and it had 4 moons that were quite happily tagging along. If Jupiter could move and keep its moons, why couldn't Earth? Galileo had found a miniature solar system, a working model of the Copernican universe, just hanging there in the darkness for anyone with a good enough telescope to see. He published his findings in March of 1610 in a little book called Sidereus Nuncius, The Starry Messenger. It's only about 60 pages. He wrote it in a matter of weeks, rushing to establish priority, and it made him famous across Europe almost overnight. In that slim volume, he described the moon's rough surface, the moons of Jupiter, and one more thing that's easy to overlook, but was genuinely stunning. He turned the telescope toward the Milky Way and resolved it into individual stars. That hazy band of light that people had wondered about for thousands of years. Democritus had guessed it might be distant stars, but nobody could prove it. Galileo pointed his 20-power telescope at it and saw stars. Thousands and thousands of stars, too faint and too close together for the naked eye to separate, but clearly, unmistakably, individual points of light. The universe was suddenly enormously larger than anyone had imagined. And here's the thing about Galileo's telescope. It wasn't very good. I mean, by our standards, it was terrible. The lenses were small, maybe an inch or so across. The glass was full of imperfections, bubbles, streaks, slight color distortions. The field of view was tiny, like looking through a soda straw. You had to hold your eye in exactly the right position, and even then, the image was sharp only in the very center. Finding an object in the sky with one of these things was genuinely difficult, and yet it was enough. It was enough to overturn 2 millennia of cosmological certainty. That's what gets me about this story. The tool was so crude, so limited, but the universe was so rich with detail, that even a tiny blurry window into it revealed revolutionary truths. But Galileo's design had a fundamental optical problem, and understanding that problem is key to understanding where telescopes went next. His design, what we now call a Galilean telescope, used a convex lens at the front, the objective, to gather light and bend it toward a focus, and a concave lens at the eyepiece to intercept those converging rays before they actually came to a focus and spread them back out into parallel beams that your eye could use. It worked, but it had serious limitations. The field of view was narrow. You couldn't make it much more powerful without making it nearly impossible to use. And it suffered badly from something called chromatic aberration. Let's talk about chromatic aberration for a second, because it's going to haunt telescope makers for the next 150 years. Remember how we talked about refraction, light bending when it passes from air into glass? Here's the catch. Light isn't just one thing. White light, sunlight, is actually a mixture of all the colors of the visible spectrum, from red through orange, yellow, green, blue, and violet. And each color bends by a slightly different amount when it passes through glass. Violet bends the most. Red bends the least. So when white light from a star passes through a simple glass lens, the lens doesn't bring all the colors to the same focus point. The violet light focuses a little closer to the lens than the red light. What you end up with isn't a crisp, sharp point of light. It's a point surrounded by fuzzy-colored halos, purple fringes, rainbow edges. The image looks smeared, and the more you try to magnify it, the worse the problem gets. This is a fundamental property of how glass interacts with light. It's not a manufacturing defect. It's not that the lens was ground wrong. It's physics. A single lens made of a single type of glass will always do this, and there's no way around it. Or at least, that's what people believed for a very long time. And that belief shaped the entire next century of telescope design in a way that's honestly kind of hilarious. But before we get there, let me tell you about Johannes Kepler, because Kepler made a crucial contribution to telescope optics, even though he never actually built a particularly good telescope himself. Kepler was an astronomer and mathematician working in Prague, and in 1611, just a year after Galileo's starry messenger, he published a treatise on optics called Dioptris. In it, he analyzed how lenses worked with a rigor that Galileo never really bothered with. Galileo was more of an observer and experimenter, while Kepler was a theorist. And Kepler proposed a different telescope design. Instead of using a concave eyepiece lens like Galileo's, Kepler suggested using a convex lens for the eyepiece too. Both lenses convex. The objective lens would bring light to an actual focus point inside the tube, and then the eyepiece lens, placed just beyond that focus, would pick up the diverging rays and make them parallel again for your eye. This had a huge advantage. The field of view was much wider. You could actually see a reasonable patch of sky at once, instead of peering through that soda straw. It also meant you could put a physical object, a crosshair, a measuring scale, a reticle, right at that internal focus point, which was enormously useful for making precise measurements. The downside? The image was flipped upside down, which for astronomy doesn't matter at all. There's no up or down in space. But it meant the Keplerian design wasn't great for terrestrial use, for looking at ships on the horizon or troops on a battlefield. Still, for astronomy, it was clearly superior, and by the middle of the 17th century, the Keplerian design had become standard. But here's what's wild. Both designs, Galilean and Keplerian, still suffered from chromatic aberration. Both used simple glass lenses, and simple glass lenses split colors, and astronomers were desperate for more magnification, more detail, more resolving power. They wanted to see the surface features of planets, to map the moon in detail, to discover new things. But every time they made the lenses more powerful, the chromatic aberration got worse. The colored fringes got bigger. The images got mushier. So someone, and this is where the story gets wonderfully absurd, someone figured out that you could reduce chromatic aberration by making the objective lens very, very gently curved. A lens with a long focal length, a very gradual curve, bends the light less sharply, and that means the colors don't spread apart as much. The aberration is still there, but it's less noticeable. The problem is, a gently curved lens means a very long focal length, which means a very long telescope. And I mean very long. In the 1650s and 1660s, astronomers started building telescopes that were 20, 30, 40 feet long. Johannes Hevelius in Gdansk built one that was 150 feet long. Think about that. 150 feet. That's half a football field. You couldn't enclose it in a tube. The tube would sag under its own weight. So Hevelius mounted the objective lens on a tall mast and connected it to the eyepiece with ropes and planks, and the whole contraption swayed in the wind. Christian Huygens, the brilliant Dutch physicist who discovered Titan, Saturn's largest moon, he and his brother built telescopes with focal lengths of over 120 feet. They eventually gave up on tubes entirely and invented what they called aerial telescopes, where the objective lens was mounted on a pole or a building, and the observer stood far away on the ground, holding the eyepiece, trying to align the two by means of a long string or a connecting rod. On a calm night, with patience, you could get it to work. On a windy night, forget it. And yet, despite how ridiculous these instruments were, they made real discoveries. Huygens discovered Titan in 1655 and figured out that the strange appendages Galileo had seen on Saturn were actually a ring system, a flat ring surrounding the planet, tilted at an angle to our line of sight, which explained why its appearance changed over the years. Giovanni Cassini, working at the Paris Observatory with long refractors, discovered 4 more moons of Saturn and found the dark gap in Saturn's rings that still bears his name, the Cassini division. These long, unwieldy, almost comically impractical telescopes were pushing the boundaries of human knowledge, one shaky, wind-buffeted observation at a time. But it was clear this couldn't go on forever. You can't just keep making telescopes longer and longer. There's a practical limit, and by the late 17th century, they were bumping up against it hard. The instruments were nearly unusable. Observations took hours of setup. A slight breeze ruined everything. Astronomers needed a fundamentally different approach, and the person who provided it, or at least who pointed the way, was someone you've almost certainly heard of, though probably not in connection with telescopes. His name was Isaac Newton, and in 1668, in his rooms at Trinity College, Cambridge, he built something that changed everything about how astronomers looked at the sky. What Newton built was small. Tiny, really. The whole instrument was only about 6 inches long, and the mirror inside it, the part that did the actual work, was just over an inch across. Compared to those monstrous 100-foot aerial telescopes, it looked like a toy. But the idea behind it was so elegant, so fundamentally right, that it would eventually lead to every major observatory telescope built from that point forward, all the way to the ones we use today. So here's what Newton understood, and it's worth slowing down to appreciate this, because it's one of those moments where someone sees a problem clearly enough to realize that the solution isn't to keep doing the same thing better. It's to do something completely different. The The problem, remember, was chromatic aberration. White light passing through a glass lens gets split into its component colors, each color bending by a slightly different amount, so you end up with colored fringes around everything you look at. And the thing is, this isn't a manufacturing defect. It's not that the lenses were poorly ground. It's a fundamental property of how light interacts with glass. Newton had actually done the experiments himself, his famous prism work, where he showed that white light is a mixture of all the colors of the spectrum. He understood better than anyone alive exactly why lenses produced those colored halos, and he was actually somewhat pessimistic about ever fixing it. He believed, incorrectly as it turned out, but we'll get to that chromatic aberration was inherent to all refraction, that any lens made of any material would always split colors by the same proportional amount. If that were true, then no clever combination of lenses could ever fully correct the problem. Now, Newton was wrong about that. About 50 years later, an English barrister and amateur optician named Chester Moore Hall figured out that you could combine two different types of glass, crown glass and flint glass, into what's called an achromatic doublet, which largely cancels out chromatic aberration. And a London optician named John Dolland later popularized and patented the design in the 1750s. But Newton didn't know that was possible. And honestly, even if he had, his solution was still brilliant on its own terms because it sidestepped the problem entirely. His insight was simple. If lenses cause chromatic aberration because they refract light, then don't use a lens to gather light. Use a mirror instead. Mirrors don't refract light, they reflect it. And reflection treats all colors of light exactly the same way. The angle of incidence equals the angle of reflection, period, regardless of wavelength. A mirror doesn't care if the light is red or blue or green. It bounces it all to the same focal point. No color splitting. No chromatic aberration. Problem solved. Well, problem partly solved. Because now you've got a new problem, and it's a practical one. If you put a curved mirror at the bottom of a tube to gather light and focus it, where do you put your head to look at the image? The focal point is somewhere up inside the tube, between the mirror and the incoming light. If you put your eye there, your head blocks the light coming in. You're literally standing in your own way. Newton's solution was clever. He placed a small flat mirror at a 45-degree angle near the focal point, and this little secondary mirror deflected the focused light sideways, out through a hole in the side of the tube, where you could attach an eyepiece and look in comfortably without blocking anything. This is the Newtonian reflector design, and it's still one of the most common telescope designs in the world. If you've ever seen an amateur astronomer's telescope where you look in from the side near the top of the tube rather than straight through the back end, that's Newton's layout, essentially unchanged after more than 350 years. Now here's the thing. Newton built his little reflector, showed it to the Royal Society in 1672, and it caused a genuine sensation. People were amazed at how sharp the images were for such a tiny instrument. It could magnify about 40 times, which isn't much by modern standards, but the image quality was noticeably better than a refracting telescope of similar size because there was no chromatic aberration. The Royal Society was so impressed, they kept it. They actually still have it, or at least a version attributed to Newton, in their collection in London. But despite the excitement, reflecting telescopes didn't immediately take over. And the reason is interesting, because it comes down to material science, to the practical reality of what you can actually make a mirror out of in the 17th century. See, Newton's mirror was made of speculum metal, an alloy of copper and tin, basically a type of bronze. You could polish it to a decent shine, and you could grind it into a curved shape. But speculum metal had serious problems. First, it tarnished. Expose it to air, and within weeks or months, the reflective surface degraded. You'd have to repolish it, and every time you repolished it, you risked changing the carefully ground curvature. Second, it was heavy. A big speculum mirror weighed enormously more than a glass lens of the same diameter. Third, and maybe most importantly, it was incredibly difficult to grind and polish to the precise curvature you needed. Making a really good parabolic mirror, and you need a parabola, not a sphere, to bring all the light to a single sharp focus, was an art form that very few people mastered. So for decades after Newton, reflecting telescopes remained somewhat exotic, somewhat unreliable. Refractors, despite their chromatic aberration, were still the workhorse instruments of astronomy. But the reflecting idea didn't die. Other people kept working on it, refining the design, trying different mirror configurations. James Gregory, a Scottish mathematician, had actually proposed a reflecting telescope design even before Newton built his, though Gregory never successfully constructed one himself. Gregory's design used a concave secondary mirror instead of Newton's flat one, bouncing the light back through a hole in the primary mirror so you could look straight through the back of the telescope. The Cassegrain design, proposed by a Frenchman named Laurent Cassegrain around 1672, used a convex secondary mirror to achieve something similar, but with a shorter tube. Both of these designs would become enormously important later, but in the 17th century, they were mostly theoretical because nobody could make mirrors good enough to realize their potential. The person who really made reflecting telescopes practical, who turned them from curiosities into serious scientific instruments, was a most unlikely figure. His name was William Herschel, and his story is one of the most remarkable in the history of science. Herschel was born in Hanover, Germany in 1738. He wasn't trained as a scientist or an engineer. He was a musician, an oboist in the Hanoverian Guards Band. He came to England as a young man, made his living as a music teacher and organist in the city of Bath, and somewhere along the way, he became obsessed with astronomy. And when I say obsessed, I mean he started making his own telescopes, not buying them, making them from scratch in his own home, casting and grinding his own speculum metal mirrors by hand. Think about what that involves. You have to melt copper and tin together at extremely high temperatures, pour the molten metal into a mold, let it cool without cracking, and then spend weeks or months grinding and polishing the resulting disc into a perfect parabolic curve, checking your work constantly against optical tests. Herschel did this over and over, hundreds of times. His sister Caroline, who was herself a remarkable astronomer, helped him through marathon grinding sessions that sometimes lasted 16 hours straight. She would literally feed him by hand while he kept polishing, because if he stopped and let the mirror cool unevenly, the work could be ruined. And here's what's wild about this. Herschel got good at it. Really, really good. By the late 1770s, he was making reflecting telescopes that were better than anything else available in England. His mirrors were more precisely figured, more highly polished, and larger than what professional instrument makers were producing. And on March 13th, 1781, using a homemade reflecting telescope with a mirror about 6¼ inches across, Herschel discovered a new planet. He was methodically surveying the sky, cataloging stars, when he noticed something that didn't look quite right. a faint object in the constellation Gemini that appeared as a small disk rather than a point of light. At first he thought it was a comet, but as other astronomers tracked its orbit over the following weeks, it became clear that this was something far more extraordinary. It was a planet orbiting the Sun well beyond Saturn. It was eventually named Uranus, and it was the first planet discovered in recorded history. Every other planet visible to the naked eye had been known since antiquity. A musician from Bath, using a telescope he'd built in his own house, had doubled the size of the known solar system. That discovery made Herschel famous overnight. King George III gave him a royal pension so he could abandon music and do astronomy full-time. And Herschel used that freedom to build bigger and bigger reflectors. His most ambitious project was a telescope with a mirror 4 feet across, 48 inches in diameter, housed in a tube 40 feet long. It was completed in 1789, and for 50 years it was the largest telescope in the world. The mirror alone weighed over 1,000 pounds. Casting it was a nightmare. One early attempt cracked during cooling and sent molten metal flooding across the workshop floor, nearly killing several workers. But when it worked beautifully. On its very first night of serious observation, Herschel discovered 2 new moons of Saturn. But even Herschel's great telescope had the fundamental limitation of speculum metal. The mirror tarnished. It needed constant repolishing. It was so heavy that pointing the telescope was a major mechanical challenge. And here's something people don't always appreciate about large telescopes. It's not just about making a big mirror. You also have to hold that mirror in exactly the right shape while it's pointing at different parts of the sky. As you tilt a large, heavy mirror, gravity pulls on it differently, and it can flex and distort, blurring the image. The mounting, the support structure, the mechanism for tracking the apparent motion of stars as the Earth rotates, all of these engineering challenges scale up dramatically as the mirror gets bigger. Herschel dealt with these problems through sheer ingenuity and brute force, but he was pushing speculum metal technology to its absolute limit. Meanwhile, refractors were getting better too. Remember Chester Moore Hall and John Dolland and the achromatic doublet? That technology kept improving throughout the 18th century. By combining crown glass and flint glass elements, lens makers could largely cancel out chromatic aberration, producing sharp, color-free images that rivaled or exceeded what reflectors could achieve at moderate sizes. And lenses had practical advantages. They didn't tarnish. They were lighter per unit of aperture than speculum mirrors, and the optical quality was more consistent. So through the late 1700s and into the 1800s, there was this ongoing competition between refractors and reflectors, each type having passionate advocates, each having genuine strengths and weaknesses. The person who pushed refractors to their ultimate expression was a Bavarian named Joseph von Fraunhofer, and his story is almost as unlikely as Herschel's. Fraunhofer was born in 1787 in Straubing, Bavaria, the 11th child of a master glazier. Both his parents died when he was young, and he was apprenticed to a mirror maker and glass cutter in Munich named Philipp Anton Weichselberger, who by most accounts treated him terribly, overworked, underfed, denied access to books or education. And then, in 1801, when Fraunhofer was 14 years old, the building where he lived and worked collapsed, just completely fell down. Fraunhofer was buried in the rubble, trapped for hours. The rescue effort was personally overseen by Maximilian Joseph, the Elector of Bavaria, essentially the ruler of the state, who happened to be nearby. When the boy was finally pulled out alive, Maximilian took a personal interest in him. He gave Fraunhofer money and, more importantly, arranged for him to receive an education and access to books on optics. And this is where the story turns, because Fraunhofer was a genius. Given the chance to learn, he devoured everything he could find about glassmaking, optics, and precision measurement. By his early 20s, he was working at the Benedict Boyern Glassworks, and he essentially reinvented the art of making optical glass. Before Fraunhofer, glass quality was wildly inconsistent. Bubbles, streaks, variations in composition that made it nearly impossible to produce large, optically perfect lenses. Fraunhofer figured out how to control the melting and cooling process so precisely that he could produce glass of unprecedented homogeneity. And then he figured out how to grind and polish that glass into lenses of a quality no one had ever achieved before. See, grinding a lens isn't just about shaping glass into a curve. It's about making that curve mathematically precise across the entire surface so that every single ray of light passing through it bends by exactly the right amount and converges to exactly the same point. Any tiny imperfection, a zone that's a little too flat here, a little too steep there, and the image gets blurry or distorted or just not as sharp as it should be. Fraunhofer developed testing methods and grinding techniques that let him control the shape of a lens surface to an accuracy that was, for his era, almost absurdly good. We're talking about deviations measured in fractions of a wavelength of light, though he wouldn't have described it that way at the time. But here's what's really remarkable. Fraunhofer didn't just make great lenses. He made great lenses and then used them to make discoveries that changed physics. While testing his glass and checking the precise way different colors of light bent through his prisms, he noticed something peculiar. When he spread sunlight into a rainbow spectrum, the same experiment Newton had done over a century earlier, he saw that the spectrum wasn't a smooth, continuous band of color. It was crossed by hundreds of fine, dark lines. Specific, sharp, dark lines at very particular positions in the spectrum, as if someone had drawn thin black threads across the rainbow. Newton had actually missed these, or at least hadn't investigated them carefully, probably because his prisms weren't good enough and his setup didn't produce a clean enough spectrum. A few other people had glimpsed hints of them, but Fraunhofer, with his superb glass and his meticulous eye, mapped out hundreds of these lines. He cataloged the most prominent ones and labeled them with letters A, B, C, D, and so on. We still call them Fraunhofer lines today. Now, Fraunhofer didn't fully understand what caused those dark lines. That explanation would come later, from people like Kirchhoff and Bunsen in the 1850s and 1860s, who showed that each chemical element absorbs light at specific wavelengths. Those dark lines in the solar spectrum are essentially the fingerprints of elements in the sun's atmosphere. Hydrogen, sodium, iron, calcium, all absorbing their signature wavelengths as sunlight passes through the cooler outer layers of the sun. This was the birth of spectroscopy, and it would eventually become one of the most powerful tools in all of astronomy. The ability to look at the light from a distant star and tell you what that star is made of, how fast it's moving, how hot it is. All of that traces back to those dark lines Fraunhofer noticed while testing his glass. But let's come back to the telescopes themselves, because that's where Fraunhofer's immediate impact was most dramatic. Using his superior glass and his precision grinding, he built refractors that were simply in a different league from anything that existed before. His masterpiece was the great Dorpat refractor, completed around 1824 for the observatory at Dorpat. That's modern-day Tartu in Estonia. It had an objective lens about 9.6 inches across, which doesn't sound enormous, but the optical quality was so high that it outperformed much larger instruments. The astronomer Friedrich Georg Wilhelm Struve used it to conduct the first major survey of double stars, cataloging thousands of binary star systems. Fraunhofer also built a heliometer for the Königsberg Observatory that was used by Friedrich Bessel to measure the first stellar parallax in 1838. The first direct measurement of the distance to a star other than the sun. That's a pretty big deal. People had been trying to measure stellar parallax since Copernicus suggested the Earth moved around the sun, and for nearly 3 centuries nobody could do it because the angles involved are so incredibly tiny. Bessel managed it with a Fraunhofer instrument, measuring the parallax of the star 61 Cygni and finding it to be about 0.314 arcseconds, which put the star roughly 10 light-years away. And the fact that he could measure an angle that's small tells you everything about the quality of the optics Fraunhofer was producing. Fraunhofer died young in 1826, at just 39 years old, probably from the toxic effects of the heavy metal fumes he'd been breathing for years while working with glass and metal. It's one of those quietly tragic details that runs through the history of science and engineering. The very work that made him brilliant was slowly killing him. But the tradition he established lived on. His techniques for making optical glass and grinding lenses were carried forward and refined, and they set the standard for the great refractors that would dominate observational astronomy for much of the 19th century. And this is where the story gets into what you might call the age of the great refractors. This period, from roughly the 1840s through the 1890s, where observatories competed to build bigger and bigger refracting telescopes, each one pushing the limits of what glass could do. Think about what's involved. To make a bigger refractor, you need a bigger objective lens. A bigger lens collects more light, which means you can see fainter objects, and it also gives you better resolving power, which means you can see finer details. But making a big lens is brutally hard. You need 2 pieces of glass. Remember, these are achromatic doublets, a crown glass element and a flint glass element, and both pieces need to be optically perfect throughout their entire volume. No bubbles, no streaks, no internal stress. Then you need to grind and polish 4 optical surfaces to exquisite precision. And the lens has to be supported only at its edges because light passes through it. You can't put anything behind it to hold it up, the way you can with a mirror. So as the lens gets bigger, it gets heavier, and it starts to sag under its own weight, which distorts its shape and degrades the image. Despite all of that, they kept building them bigger. The Pulkovo Observatory near St. Petersburg got a 15-inch refractor in 1839. Then came an 18.5-inch refractor at the Dearborn Observatory in Chicago in 1862, built by the American firm of Alvin Clark and Sons. And here's a wonderful detail about the Clarks. Alvin Clark was originally a portrait painter who became interested in optics and started grinding lenses essentially as a hobby. He turned out to be extraordinarily talented at it, and his firm became the premier maker of large refracting telescopes in the world. His son, Alvin Graham Clark, while testing the 18.5-inch lens for the Dearborn telescope in 1862, pointed it at Sirius, the brightest star in the sky, and spotted a tiny, faint companion star right next to it. This was Sirius B, the white dwarf companion that had been predicted mathematically by Bessel back in 1844 based on wobbles in Sirius's motion. But nobody had ever actually seen it. Alvin Graham Clark found it while testing a lens. That's the kind of thing that happens when your optics are good enough. The Clarks kept going. a 26-inch refractor for the U.S. Naval Observatory in 1873, which was used to discover the two moons of Mars, Phobos and Deimos, by Asaph Hall in 1877. Then a 30-inch refractor for Pulkovo. Then the 36-inch refractor for Lick Observatory on Mount Hamilton in California, completed in 1888. And finally, the crown jewel, the 40-inch refractor at Yerkes Observatory in Williams Bay, Wisconsin, completed in 1897. The Yerkes refractor remains the largest refracting telescope ever built, 40 inches across. The lens alone weighs about 500 pounds. The tube is 63 feet long. The entire moving assembly weighs about 20 tons. And the building that houses it has a 90-foot dome. Here's the thing about the Yerkes telescope, though. It wasn't just the biggest refractor. It was essentially the last great refractor, because it ran right into the wall of physical limits. At 40 inches, the lens was about as big as a refracting telescope could practically go. Any larger, and the glass would sag too much under its own weight. You can only support a lens at its edges, remember, so the center of a very large lens literally droops, changing its shape in ways you can't correct. The glass also absorbs some light. No glass is perfectly transparent. And the thicker the lens, the more light you lose. And there's still chromatic aberration. The achromatic doublet reduces it enormously, but it doesn't eliminate it completely. With a 40-inch lens, even that residual color fringing becomes noticeable. So by the late 1890s, the refractor had reached its ceiling. And this is where the story pivots back to reflectors, because mirrors don't have any of these problems. A mirror can be supported from behind. You can put all sorts of supports across the entire back surface to prevent sagging. Light doesn't pass through a mirror, so there's no absorption in the glass and no chromatic aberration at all. The only surface that matters is the front reflecting surface, so you only need to grind and polish one curve instead of 4. In principle, you can build a reflecting telescope much, much larger than any refractor. The person who proved this wasn't just theoretical, was a wealthy Irishman named William Parsons, the 3rd Earl of Ross. And his story is one of those wonderful examples of what happens when you combine serious engineering talent with essentially unlimited funding and a willingness to try things that everyone else thinks are crazy. Parsons was obsessed with building large reflecting telescopes, and in the 1840s, at his estate at Birr Castle in central Ireland, he built what became known as the Leviathan of Parsonstown, a reflecting telescope with a mirror 72 inches across, 6 feet. This was in 1845, more than 50 years before the Yerkes refractor, and the mirror was nearly twice the diameter. He cast the speculum metal mirrors himself in a furnace he built on his estate, using turf, peat, as fuel, with a crew of laborers helping him maneuver these enormous, fragile metal discs. The Leviathan was an extraordinary instrument, but it was also deeply flawed in ways that tell you a lot about the engineering challenges of large telescopes. The mirror weighed about 3 tons. It was mounted between 2 massive stone walls that acted as supports, which meant the telescope could only swing north and south along a narrow strip of sky near the meridian. It couldn't point freely in all directions. And this was Ireland, so the weather was terrible. Clear nights were rare. The speculum metal mirror tarnished, as speculum always does, and had to be periodically removed and repolished, which meant the telescope was frequently out of commission. Despite all of that, Parsons made a genuinely important discovery with it. In 1845, he pointed it at a fuzzy patch of light that had been catalogued as a nebula, Messier 51, and for the first time, he could see that it had a spiral structure. He drew it, and his drawing clearly shows the spiral arms. This was the first time anyone had seen spiral structure in what we now know as a galaxy. He didn't know it was a galaxy. That understanding wouldn't come for another 80 years. But he saw the shape, and that observation would eventually become a crucial piece of evidence in one of the biggest debates in the history of astronomy. But the Leviathan also showed, almost painfully, that just making a big mirror wasn't enough. You needed good optics, a good mounting that let you point the telescope anywhere in the sky and track objects smoothly as the Earth rotated, a good sight with clear skies and steady air, and a mirror material that didn't degrade. Speculum metal was still the only option for mirrors, and it was still terrible, heavy, prone to tarnishing, and incredibly difficult to cast and grind at large sizes. What reflectors really needed was a completely different kind of mirror, and that breakthrough was already taking shape in the mind of a German chemist named Justus von Liebig, who in 1835 had developed a process for depositing a thin layer of silver onto glass. It took a few decades for anyone to think of applying this to telescope mirrors, but when they did, it changed everything. A French physicist named Léon Foucault, you might know his name from the Foucault pendulum, that beautiful demonstration of the Earth's rotation, he was the one who really made the connection. In 1857, Foucault took Liebig's silver-on-glass technique and applied it to a telescope mirror, and the advantages were immediately obvious. Think about what this meant. Instead of casting a massive, heavy chunk of speculum metal and then grinding a curve into it, a process that took months and could fail catastrophically at any step, you could now start with a piece of glass. Just glass. You'd grind and polish the glass into the right concave shape, which was much easier because glass is a far more cooperative material to work with. It's lighter, it's more rigid for its weight, and it holds its shape better. Then, once you had your perfectly curved glass surface, you'd chemically deposit a thin coating of silver onto it. That silver layer was your reflective surface. And here's the beautiful part. If the silver tarnished, and silver does tarnish, though not nearly as badly as speculum metal, you didn't have to regrind the entire mirror. You just stripped off the old silver coating and applied a new one. The glass underneath, with its carefully figured curve, was untouched. You could recoat a mirror in a day. Compare that to the weeks or months it took to repolish a speculum metal mirror, during which you might accidentally change the curve and ruin the whole thing. The difference in reflectivity alone was dramatic. Speculum metal, when freshly polished, reflected maybe 60 to 65% of the light hitting it. Silver on glass reflected over 90%. That's a huge jump. It meant a silvered glass mirror of a given size could see fainter objects than a speculum mirror of the same size. Or to put it another way, a smaller silvered mirror could match the performance of a much larger speculum one. And the weight savings were enormous. Glass is dense, sure, but nothing like the copper-tin alloy of speculum metal. A glass mirror could be made much thinner relative to its diameter, which meant the telescope structure supporting it didn't need to be as massive, which meant the mounting could be more manageable, which meant you could actually point the thing where you wanted. Foucault demonstrated this with relatively small mirrors at first, but the principle scaled up beautifully. And within a couple of decades, silvered glass had completely replaced speculum metal for serious astronomical mirrors. It was one of those transitions that seems obvious in retrospect, but took surprisingly long to happen. Liebig published his silver-on-glass process in 1835. Foucault applied it to telescopes in 1857. That's 22 years of the technique just sitting there, waiting for someone to make the connection. Sometimes the pieces of a breakthrough exist for years before anyone puts them together. Now, there's another thing Foucault contributed that's worth lingering on, because it's one of those elegantly simple ideas that solves a problem people had been struggling with for centuries. How do you test whether your mirror is the right shape? You've spent weeks grinding and polishing this piece of glass, trying to get a perfect parabolic curve. How do you actually check? Before Foucault, the main method was to point the telescope at a star and see if the image looked good, which is a terrible way to test optics because atmospheric turbulence blurs everything, and you can't tell whether the fuzziness is from your mirror or from the air. Foucault invented what's now called the Foucault knife edge test. The idea is deceptively simple. You set up a point source of light, a tiny pinhole illuminated by a lamp, at the center of curvature of the mirror, which is twice the focal length away. The light goes out to the mirror, bounces back, and comes to a focus right next to the light source. Now, at that focus point, you slowly slide a knife edge, literally a sharp blade, across the returning cone of light. And here's what happens. If the mirror is a perfect sphere, the entire mirror will appear to darken uniformly as the knife cuts across the light. But if there are any bumps or hollows or zones on the mirror's surface, even incredibly tiny ones, fractions of a wavelength of light, they'll show up as shadows and bright spots on the mirror's face. You can actually see the errors. A bump will appear to cast a shadow on one side, a hollow on the other. It's astonishingly sensitive. You can detect surface errors of just a few millionths of an inch. This test gave mirror makers, for the first time, a reliable, precise way to check their work as they went. Grind a little, test. Polish a little, test. It turned mirror making from a kind of dark art into something approaching a science. And it's still used today. Amateur telescope makers in their garages and backyards use the Foucault test to figure their mirrors. It's been around since the 1850s, and nothing has fundamentally replaced it for simplicity and effectiveness. That's a remarkable run for any piece of technology. So by the 1870s and 1880s, you had silvered glass mirrors, you had the Foucault test, and you had a growing understanding that the future of big telescopes was in reflectors, not refractors. The Yerkes 40-inch refractor of 1897 would be the last hurrah for the big lenses, remember, the absolute physical limit. But reflectors could, in principle, keep getting bigger. Glass mirrors could be made larger than glass lenses because a mirror only needs to be supported from behind, while a lens can only be held at its edges and will sag under its own weight. And mirrors don't have chromatic aberration at all, because the light never passes through the glass. It just bounces off the silvered surface. All those problems that had plagued refractors for centuries simply didn't apply. The person who really proved this, who showed that the future of astronomy belonged to large reflectors on mountaintops, was George Ellery Hale. And Hale is one of those figures who keeps showing up at every major turning point, like he had some kind of sixth sense for where astronomy needed to go next. He was born in Chicago in 1868, the son of a wealthy elevator manufacturer. His father made a fortune building the elevators for the skyscrapers that were going up all over Chicago in the building boom after the Great Fire. So, Hale grew up with money, which mattered enormously because his real genius wasn't just in science, it was in fundraising. He had an almost supernatural ability to convince very rich people to pay for very expensive telescopes. Hale was the driving force behind the Yerkes 40-inch refractor. he convinced the streetcar magnate Charles Yerkes to fund it. But even as that great refractor was being built, Hale was already thinking about reflectors. He understood that the next leap in astronomy required bigger apertures, and bigger apertures meant mirrors. In 1904, he convinced the Carnegie Institution to fund a 60-inch reflector on Mount Wilson, above Pasadena, California. The site selection was deliberate and important. Hale understood something that the Leviathan at Burr Castle had demonstrated so painfully. It doesn't matter how big your telescope is if the air above it is turbulent and the sky is cloudy. Mount Wilson, at about 5,700 feet elevation, sat above much of the atmospheric turbulence of the Los Angeles basin, and Southern California had reliably clear skies. The site was transformative. For the first time, a large telescope was placed where the seeing, that's the astronomer's term for atmospheric steadiness, was genuinely good. The 60-inch saw first light in 1908, and it was immediately the most powerful telescope in the world. The mirror was made of plate glass, not the best material, as it turned out, because plate glass expands and contracts with temperature changes, which distorts the mirror's shape over the course of a night. But even with that limitation, the 60-inch was a revelation, and Hale was already planning something bigger. He went to John D. Hooker, a Los Angeles businessman, and convinced him to fund a 100-inch reflector. 100 inches. That's over 8 feet across. The mirror blank was cast by a French glassworks, the Saint-Gobain company, and the casting was a nightmare. The first attempt produced a disc riddled with bubbles and imperfections. Saint-Gobain tried again, and the second disc was better but still not perfect. It had bubbles trapped inside the glass. There was a real debate about whether it was usable. Hale decided to go ahead with it anyway, and the grinding and polishing took years. The 100-inch Hooker telescope saw first light on November 2nd, 1917, and it would remain the largest telescope in the world for the next 3 decades. And this is where the story gets really profound, because the discoveries made with the Hooker 100-inch didn't just advance astronomy. They fundamentally changed humanity's understanding of its place in the universe. The person who made those discoveries was Edwin Hubble, and his story is inseparable from this telescope. Hubble arrived at Mount Wilson in 1919, fresh from military service in World War I. He was tall, athletic, a former boxer and Rhodes Scholar, a bit of a showman, honestly, who affected a British accent despite being from Missouri. But he was also a brilliant observer, patient and meticulous. Remember Lord Rosse and the spiral nebulae? Remember how Rosse had seen spiral structure in M51 back in 1845 but didn't know what it was? By the 1920s, there was a raging debate in astronomy about what those spiral nebulae actually were. One camp, led by Harlow Shapley, argued that they were just clouds of gas within our own Milky Way galaxy, and that the Milky Way was essentially the entire universe. The other camp, championed by Heber Curtis, argued that the spiral nebulae were actually separate galaxies, island universes, they called them, vast collections of stars far beyond our own. This was the great debate, and it was held formally at the Smithsonian in April 1920. Neither side could prove their case because nobody had been able to measure the distance to a spiral nebula. Hubble changed that. Using the 100-inch Hooker telescope, he spent years photographing the Andromeda Nebula, Messier 31, and in October 1923, he found what he was looking for: a Cepheid variable star. Cepheids are stars that pulsate, brightening and dimming in a regular cycle, and there's a tight relationship between how fast a Cepheid pulsates and how intrinsically bright it is. Henrietta Swan Leavitt had discovered this relationship back in 1908 by studying Cepheids in the Magellanic Clouds, and it gave astronomers a cosmic yardstick. If you could find a Cepheid, measure its pulsation period, and calculate its true brightness, then compare that to how bright it appeared from Earth, you could figure out how far away it was. Hubble did exactly that. He measured the Cepheid in Andromeda, calculated the distance, and the answer was staggering, roughly 900,000 light-years. The Milky Way itself was estimated to be about 100,000 light-years across. Andromeda was far, far beyond the edge of our galaxy. It wasn't a nebula at all. It was another galaxy entirely. The universe, in that moment, got unimaginably bigger. And it was the telescope that made it possible, specifically, the combination of a large mirror that could gather enough light to resolve individual stars in another galaxy, a good sight with steady air, and the patient skill of the observer. Everything that had been learned and built and refined over the preceding 3 centuries, the optics, the mirror technology, the mountings, the site selection, all of it converged in that single observation. But Hubble wasn't done. Having established that the universe was full of galaxies, he started measuring how fast those galaxies were moving, using spectroscopy, the same basic science that had grown out of Fraunhofer's dark lines. When you look at the spectrum of a distant galaxy, the absorption lines are shifted toward the red end of the spectrum if the galaxy is moving away from us. The faster it's receding, the greater the shift. And what Hubble found, working with Milton Humason, a former mule driver turned astronomer who was one of the most skilled observers who ever lived, was that almost every galaxy they measured was moving away from us. And the farther away a galaxy was, the faster it was receding. This was Hubble's law, published in 1929, and it meant something almost incomprehensible. The universe itself was expanding. Every galaxy was rushing away from every other galaxy, like dots painted on the surface of a balloon that's being inflated. This was the observational evidence for what would become the Big Bang Theory, the idea that the universe began in an incredibly hot, dense state and has been expanding ever since. And all of it, every bit of it, came from light gathered by a 100-inch glass mirror coated in silver, sitting on a mountaintop in California. Hale, meanwhile, was already dreaming of something even larger. Even before the Hooker telescope had made its greatest discoveries, he was thinking about a 200-inch mirror. 200 inches, that's almost 17 feet across. And the engineering challenges of building such a thing were enormous, almost absurd. Think about what Hale was proposing. The Hooker's 100-inch mirror had nearly broken everyone involved: the casting, the transport, the figuring, the mounting. And now he wanted to double the diameter. But here's the thing about doubling the diameter of a mirror. You don't just get twice the light-gathering power. You get 4 times. Because light-gathering ability scales with the area of the mirror, and area scales with the square of the diameter. A 200-inch mirror would collect 4 times as much light as the 100-inch, which meant it could see objects 4 times fainter, which meant it could peer twice as far into the universe. That was the prize. And Hale wanted it badly. He started lobbying for the project in the early 1920s, and in 1928, he secured $6 million from the Rockefeller Foundation, an absolutely staggering sum at the time, equivalent to something like $100 million today. The project was assigned to Caltech, and the telescope would be built on Palomar Mountain, about 90 miles southeast of Los Angeles, at an elevation of roughly 5,600 feet. The site was chosen carefully. the way Hale had always chosen his sites. Dark skies, steady air, minimal light pollution. At the time, Palomar was remote enough that the glow of cities wasn't a problem. That would change eventually, but in the 1930s, it was ideal. Now the first and most daunting challenge was the mirror itself. 200 inches of glass, figured to a precise paraboloid, and it had to be rigid enough to hold its shape no matter which direction the telescope was pointed. With the Hooker, they'd used plate glass, and even that had been problematic. Plate glass expands and contracts with temperature changes, and when you're trying to hold a surface accurate to a fraction of a wavelength of light, thermal expansion is your enemy. So for the 200-inch, they needed something better. The material they chose was Pyrex, a borosilicate glass developed by Corning Glass Works. Pyrex has a much lower coefficient of thermal expansion than ordinary glass, roughly 1/3 as much. That meant the mirror would respond more slowly to temperature changes and distort less as the night air cooled. But casting a 200-inch disc of Pyrex was something nobody had ever attempted. Corning had to build special facilities just for the job. The disc wasn't going to be a solid slab. That would have been impossibly heavy and would have taken forever to reach thermal equilibrium with the surrounding air. Instead, they designed it as a ribbed structure, with a waffle-like pattern of support ribs on the back and a continuous faceplate on the front. Think of it like an I-beam in construction. You get most of the rigidity with a fraction of the weight. The finished disc would weigh about 20 tons, which sounds enormous, but a solid disc of the same diameter would have weighed around 40. The first attempt at casting, in March 1934, was a disaster. They poured molten Pyrex at about 2,800 degrees Fahrenheit into a ceramic mold fitted with internal cores that would create the ribbed structure on the back. But during the pour, several of the cores broke loose from the bottom of the mold and floated up into the molten glass. The disc was ruined before it even cooled. They had to start over. The second attempt, in December 1934, went better. The pour succeeded, and then began one of the most agonizingly slow processes in the history of engineering: the annealing. You can't just let a 20-ton disc of glass cool on its own. If you did, the outside would cool faster than the inside, setting up internal stresses that would crack the disc, or, even if it survived, would cause it to distort unpredictably when you tried to figure the surface. So the disc had to be cooled at an incredibly controlled rate inside a specially built annealing oven. The process took 11 months, almost a full year, just to cool a piece of glass. Think about that. Every day for 11 months, engineers at Corning were monitoring the temperature of this disc, nudging it down fraction by fraction, making sure the entire mass reached thermal equilibrium uniformly. When the disc finally emerged and was inspected, it wasn't perfect. There were some flaws, some places where the cores had shifted slightly, but it was usable. And in March 1936, it began its journey from Corning, New York to Pasadena, California. The trip itself became a national event. The disc traveled by rail on a specially designed railcar, and the train moved at no more than 25 miles per hour to minimize vibration. Crowds gathered along the route to watch it pass. It was, in a very real sense, the most famous piece of glass in the world. Once the disc arrived at Caltech's optical shop, the real work began: grinding and polishing and figuring the surface into a perfect paraboloid. And this is where you really appreciate what figuring means at this scale. The surface of the 200-inch mirror had to be accurate to about 2 millionths of an inch. If you scaled the mirror up to the size of the continental United States, the largest bump on its surface would be about 6 inches tall. That's the level of precision they were aiming for, on a piece of glass 17 feet across. The man in charge of the optical work was Marcus Brown, and later John Anderson and others, working under the overall direction of the project. They used techniques that would have been recognizable to Foucault, grinding with progressively finer abrasives, testing with light, polishing, testing again, but at a scale and precision that pushed everything to the limit. And then the war intervened. When the United States entered World War II in December 1941, the 200-inch project was put on hold. The optical shop was repurposed for military work, and the mirror sat, partially figured, for years. The war delayed the project enormously, and it also took George Ellery Hale himself. He had died in 1938, a decade before his telescope would see first light. He never saw it finished. The telescope was named after him, the Hale telescope. And it's one of those bittersweet things in the history of science that the person who willed something into existence through sheer force of vision and persuasion didn't live to see it work. After the war, work resumed, and the mirror was finally completed and installed in 1947. First light, the first time starlight hit the finished mirror and formed an image, came on January 26, 1949. And it worked. It worked beautifully. The Hale telescope was the largest effective optical telescope in the world, and it would hold that title for decades, until 1975, when the Soviet Union completed their 6-meter telescope in the Caucasus Mountains, though that instrument was plagued with problems and never really performed to its potential. In practical terms, Palomar's 200-inch remained the most scientifically productive large telescope in the world for nearly half a century. Now, here's something worth pausing on, because it connects to a problem we touched on much earlier. Remember how Newton's reflector solved the chromatic aberration problem that plagued refractors? Well, reflectors have their own optical issues, and one of the most significant is called coma. Coma is an off-axis aberration. It means that stars near the edge of the field of view don't focus to neat points, but instead get smeared into little comet-shaped blurs, which is actually where the name comes from, the same root as comet. For a simple paraboloidal mirror, coma gets worse the farther you go from the center of the field. This limits the useful field of view, which matters a lot if you're trying to photograph large swaths of sky. In 1930, an optical designer named Bernhard Schmidt, working in Hamburg, came up with an incredibly elegant solution. He took a spherical mirror, not a parabolic one, and placed a specially shaped glass corrector plate at the center of curvature of the mirror. The corrector plate is a thin lens with a complex curve that compensates for the spherical aberration of the mirror. The result is an optical system with an enormous, sharp field of view and virtually no coma. It's called a Schmidt camera, and it revolutionized survey astronomy. The Palomar Observatory Sky Survey, conducted in the 1950s using a 48-inch Schmidt camera on Palomar Mountain, photographed the entire sky visible from Southern California and became one of the most important astronomical references of the 20th century. Astronomers used those photographic plates for decades. Schmidt himself is another one of those fascinating, slightly tragic figures. He was Estonian, largely self-taught in optics, and he had lost his right hand in a childhood accident. Some accounts say it was a pipe bomb experiment gone wrong when he was a teenager. He figured the corrector plate for his first Schmidt, camera by hand, working alone, using methods he largely invented himself. He struggled with depression and alcoholism, and he died in 1935, just 5 years after his invention, never fully seeing how transformative it would become. But the Schmidt design pointed towards something important in telescope engineering. The idea that you could combine lenses and mirrors in the same system, using each to correct the flaws of the other. This is called a catadioptric design, and it opened up a whole family of telescope configurations. The Schmidt-Cassegrain, which combines Schmidt's corrector plate with a Cassegrain mirror arrangement, became one of the most popular telescope designs for amateur astronomers starting in the 1960s and 1970s because companies like Celestron and Meade figured out how to mass-produce them affordably. If you've ever looked through a backyard telescope at a star party, there's a good chance it was a Schmidt-Cassegrain. Compact, versatile, relatively inexpensive. It's the design that brought serious optics to ordinary people. Meanwhile, back at the professional level, the decades after Palomar saw a quiet revolution in how telescopes detected light. For almost the entire history of the telescope, from Galileo onward, the detector was either the human eye or, starting in the late 19th century, photographic film. And both of those detectors are, frankly, terrible. Your eye captures maybe 1 to 5% of the photons that hit it. Photographic emulsion does a bit better, maybe 2 to 4% for the best plates. That means the vast majority of the light your telescope so carefully gathers is simply wasted, never converted into useful information. The technology that changed everything was the charge-coupled device, the CCD. It was invented in 1969 at Bell Labs by Willard Boyle and George Smith. They'd later win the Nobel Prize for it. And by the late 1970s, astronomers were beginning to attach CCDs to telescopes. A CCD is a silicon chip divided into a grid of tiny picture elements, pixels, and here's what makes it magical. When a photon hits a pixel, it knocks loose an electron through the photoelectric effect, the same physics Einstein explained in 1905. Those electrons accumulate during an exposure, and then they're read out electronically, pixel by pixel, to build up a digital image. The quantum efficiency of a good CCD can reach 70, 80, even 90% or more. Compare that to the 2% of photographic film. Switching from film to CCD was like upgrading from a bucket with a hole in it to a proper cistern. Suddenly, almost every photon your mirror collected was actually being counted. A telescope that had been working at, say, 2% efficiency with film was now working at 80 or 90%. That's not a small improvement. That's a factor of 40 or more. It meant that a modest telescope equipped with a CCD could outperform a much larger telescope still using photographic plates. It meant that exposure times dropped dramatically. Observations that once required hours of patient guiding, keeping the telescope locked on a target while the Earth turned beneath it, could now be done in minutes. And because the output was digital, just numbers in a grid, you could process it with computers, stack multiple exposures, subtract out noise, extract spectra automatically. The CCD didn't just make telescopes more sensitive. It made astronomy quantitative in a way it had never been before. And this matters for what came next, because the generation of telescopes built from the 1990s onward was designed from the ground up to take advantage of digital detectors. These weren't just bigger versions of Palomar. They were fundamentally rethought. Here's the thing about building bigger telescopes. For most of the 20th century, the assumption was that you needed a single, monolithic mirror, one big slab of glass, ground and polished to perfection. The 200-inch at Palomar was the ultimate expression of that idea, and it basically hit the wall. Making a single mirror much larger than 5 meters was impractical. The glass would sag under its own weight as the telescope tilted to point at different parts of the sky. You'd need the mirror to be incredibly thick to stay rigid, which meant incredibly heavy, which meant an incredibly massive and expensive mounting structure to move it around. The whole thing scaled terribly. Engineers call this the square-cube law problem. As you double the diameter of a mirror, its weight goes up roughly as the cube, but its light collecting area only goes up as the square. Every generation of bigger mirror was proportionally heavier, stiffer, more expensive, and harder to build than the last. So after Palomar, telescope sizes essentially stalled for decades. The Soviet Union built a 6-meter telescope, the BTA-6, which saw first light in 1975 in the Caucasus Mountains. It was the largest in the world, technically, but it was plagued with problems. The mirror was made of conventional glass rather than something with low thermal expansion. The site had mediocre seeing conditions, and the dome design trapped warm air that blurred the images. It never really performed up to its aperture. In many ways, the 200-inch Hale telescope, completed 26 years earlier, remained the more scientifically productive instrument. That tells you something. Bigger isn't automatically better if you can't control all the other factors. The breakthrough that unlocked the next era came from two related ideas, and both of them are beautiful in their cleverness. The first was segmented mirrors. Instead of one giant piece of glass, what if you made a large mirror out of many smaller pieces, fitted together like a honeycomb? Each segment could be relatively thin and lightweight, and you could support each one individually with actuators, little motorized pistons that push and pull on the back of each segment to keep it in exactly the right shape and alignment. The person most responsible for making this work was Jerry Nelson, a physicist at the University of California. Starting in the late 1970s, Nelson championed the idea of a 10-meter telescope built from 36 hexagonal mirror segments, each about 1.8 meters across. People thought he was out of his mind. The segments would have to be aligned to each other with a precision of nanometers, billionths of a meter. While the telescope was moving, while the temperature was changing, while the wind was blowing. Each segment wasn't even a simple concave shape. Because they were all pieces of a single large parabolic surface, but sitting at different positions across that surface, each hexagonal segment had a slightly different, asymmetric curvature. They called this stressed mirror polishing. They'd actually warp each blank with carefully calculated forces while polishing it as a sphere. And then, when the forces were released, the glass would spring into the correct off-axis shape. It's one of those ideas that sounds almost too clever to work, but it did work. The result was the Keck 1 telescope on Mauna Kea in Hawaii, which saw first light in 1993. 10 meters of aperture, 4 times the light collecting area of Palomar. And then Keck 2 followed in 1996, a twin sitting right next to it. The two Keck telescopes could even be used together as an interferometer, combining their light to achieve the angular resolution of a telescope as wide as the distance between them, about 85 meters. That's an astonishing trick, and it connects back to the wave nature of light that we talked about much earlier. The same interference principles that cause chromatic aberration and diffraction also let you do interferometry if you're clever enough. The second big idea was active optics, and it's closely related. Even if you build a mirror from a single piece of glass, you can make it much thinner and lighter than the old Palomar approach, as long as you actively control its shape in real time. A thin mirror will flex and sag, sure, but if you put hundreds of actuators behind it, and you have a computer monitoring the image quality and constantly adjusting those actuators to push the mirror back into its ideal shape, then the flexibility becomes a feature rather than a bug. You get a lightweight mirror that's always in perfect shape, because the computer won't let it be anything else. This was the approach pioneered by the European Southern Observatory's New Technology Telescope, or NTT, which saw first light in 1989 in Chile. Its 3.5-meter mirror was deliberately made thin, only about 24 centimeters thick, compared to the Hale's mirror, which was about 60 centimeters thick at a much larger diameter. 75 actuators supported the NTT's mirror and adjusted its shape based on continuous analysis of star images. The results were stunning. The NTT consistently delivered sharper images than much larger telescopes that relied on passive, thick mirrors. Now here's where it gets really interesting, because there's a step beyond active optics, and it tackles a problem that had haunted ground-based astronomy since the very beginning: the atmosphere. You know how stars twinkle? That's not the stars doing anything. That's turbulence in Earth's atmosphere bending and distorting the light on its way down to you. The air is made up of cells at slightly different temperatures, and those temperature differences create tiny variations in the refractive index, and the light waves get scrambled as they pass through. Astronomers call this seeing, and even at the best sites in the world, mountaintops in Chile, Hawaii, the Canary Islands, the atmosphere limits your resolution to roughly 1 arcsecond. That means no matter how big your mirror is, you can't see details finer than about 1 arcsecond from the ground. A 10-meter telescope, in theory, should resolve details about 20 times finer than that, but the atmosphere smears everything out. You've built this incredible mirror, and the sky itself is the bottleneck. The solution is adaptive optics, and the story of how it came to astronomy is fascinating because it was originally a military secret. The basic concept was proposed by Horace Babcock in 1953, the same Babcock who was director of Mount Wilson and Palomar. He imagined a deformable mirror that could flex hundreds of times per second to counteract atmospheric turbulence in real time. But the technology to actually do it didn't exist in the 1950s. You'd need a wavefront sensor to measure exactly how the atmosphere was distorting the incoming light at any given instant, a fast computer to calculate the corrections, and a deformable mirror that could change shape in milliseconds. None of those things were available. The military, however, had a very strong motivation to figure this out. They wanted to image Soviet satellites from the ground, and they wanted to focus laser beams through the atmosphere for various purposes you can probably guess. So starting in the 1970s and through the 1980s, classified programs at places like the Starfire Optical Range in New Mexico developed working adaptive optics systems. When some of this technology was declassified in the early 1990s, astronomers jumped on it. The way adaptive optics works is genuinely beautiful. You point your telescope at your target, but you also need a bright reference point near it, a guide star, to measure the atmospheric distortion. A wavefront sensor, often a Shack-Hartman sensor, samples the incoming light from this guide star across the telescope's aperture and figures out exactly how the wavefront has been scrambled by the atmosphere. That information goes to a computer, which calculates the inverse distortion, the shape the deformable mirror needs to take to undo what the atmosphere just did. The deformable mirror, which sits in the light path, flexes into that shape, and this whole loop happens hundreds of times per second, constantly chasing the turbulence. But there's a catch. You need a guide star, and it has to be bright and close to whatever you're actually trying to observe. Natural bright stars aren't always conveniently located near your target. So astronomers came up with something wild: laser guide stars. You shoot a powerful laser beam up into the sky, and about 90 kilometers up, It excites sodium atoms that are left over from tiny meteorites burning up in the mesosphere. Those sodium atoms glow, creating an artificial star right where you need it. You use that artificial star as your reference for the adaptive optics system. The first astronomical laser guide star systems came online in the mid-1990s, and they transformed what ground-based telescopes could do. With adaptive optics, a large ground-based telescope can achieve resolution close to its theoretical diffraction limit, the sharpness set by the size of its mirror, and the wavelength of light, rather than by the atmosphere. The Keck telescopes with adaptive optics can take images nearly as sharp as the Hubble Space Telescope in certain wavelengths, and they have 4 times the collecting area. The Very Large Telescope in Chile, operated by ESO, 4 8.2-meter mirrors that can work independently or together, routinely uses adaptive optics to image exoplanets, the supermassive black hole at the center of our galaxy, and the surfaces of other stars. Andrea Ghez and Reinhard Genzel used adaptive optics on Keck and the VLT respectively to track stars orbiting that central black hole, Sagittarius A star, and their measurements proved it was a black hole of about 4 million solar masses. They shared the Nobel Prize in 2020 for that work. And none of it would have been possible without adaptive optics turning the atmosphere from an enemy into a manageable nuisance. So by the early 2000s, the state of the art in ground-based astronomy had been completely transformed compared to the Palomar era. Segmented mirrors, active optics, adaptive optics, CCD detectors, each of these technologies multiplied the power of the others. And all of this was happening while a completely different approach to the atmospheric problem was being pursued in parallel, one that Lyman Spitzer had first proposed back in 1946, put the telescope above the atmosphere entirely. The story of space telescopes is its own epic, and the most famous one, the one that became a household name, and also one of the most dramatic engineering stories of the 20th century, had been in the works for decades before it ever left the ground. The Hubble Space Telescope. Even the name carries a kind of weight, doesn't it? Named after Edwin Hubble, the man who proved the universe was bigger than anyone imagined and that it was expanding, the same Hubble who peered through the Hooker telescope on Mount Wilson and changed everything. Naming this telescope after him was a statement of ambition. And the story of how it came to be, how it almost became the greatest embarrassment in the history of science, and how it was rescued in one of the most extraordinary feats of engineering ever performed in orbit. That story is worth savoring. Lyman Spitzer was an astrophysicist at Yale and later Princeton, and in 1946 he wrote a paper called Astronomical Advantages of an Extraterrestrial Observatory. He was 32 years old. In that paper, he laid out the case with remarkable clarity. Up above the atmosphere, a telescope would have no seeing, no turbulence blurring the images. It could observe in ultraviolet and infrared wavelengths that the atmosphere absorbs before they ever reach the ground. And it could achieve the full diffraction-limited resolution that its mirror size allowed, all the time, not just on the rare nights when the atmosphere happened to cooperate. Spitzer spent the next 5 decades advocating for a space telescope. He lived long enough to see it fly. Barely. He died in 1997, 7 years after Hubble's launch, and 4 years after the repair mission that saved it. But we're getting ahead of ourselves. The project that became Hubble started gaining real momentum in the 1970s. NASA and the European Space Agency partnered on it. The design called for a 2.4-meter primary mirror, not enormous by ground-based standards, but remember, above the atmosphere, without seeing, a 2.4-meter mirror could outperform much larger ground-based telescopes in sharpness. The mirror was made by Perkin-Elmer, a company with deep experience in precision optics, particularly for spy satellites. And here's where the story takes its fateful turn. The primary mirror for Hubble was one of the most precisely figured mirrors ever made. It had to be. The whole point was diffraction-limited performance, and that meant the surface had to be accurate to about a 65th of a wavelength of visible light. We're talking about errors no larger than about 10 nanometers. The mirror was polished to extraordinary precision. The problem was that it was polished to the wrong shape. During the grinding and polishing process, Perkin-Elmer used a device called a null corrector to test the mirror's shape. A null corrector is an optical assembly, a set of lenses or mirrors that produces a specific wavefront. You shine light through the null corrector onto the mirror you're testing, and if the mirror is the right shape, the reflected light comes back perfectly flat, perfectly null. Any deviation from the desired shape shows up as interference fringes. It's an incredibly sensitive test. But here's the thing. The null corrector itself has to be assembled with extreme precision. If the null corrector is wrong, then you'll polish the mirror to the wrong shape, and the test will tell you everything looks perfect the whole time. That's exactly what happened. A single lens in the null corrector was positioned about 1.3 millimeters too far from where it should have been. 1.3 millimeters. And because of that tiny error in the testing device, the Hubble primary mirror was polished with a spherical aberration. The edges of the mirror focused light to a slightly different point than the center. The mirror was the wrong shape by about 2 microns at its edge, 2 millionths of a meter. It was, in a certain perverse sense, one of the most precisely wrong mirrors ever made. It was smooth and flawless, just flawlessly wrong. Now, there were other tests that could have caught this. Perkin-Elmer had 2 additional null correctors, and both of them showed that something was off. But the project managers dismissed those results, trusting the primary null corrector. There were also independent checks that could have been performed, simple end-to-end tests of the complete optical system. But schedule pressure and budget constraints meant those tests were skipped or deemed unnecessary. The decision not to perform a full end-to-end optical test of the assembled telescope before launch is one of the most consequential cost-saving decisions in the history of engineering. It saved a few $1,000,000. The repair mission that eventually fixed the problem cost over $700 million. Hubble launched on April 24, 1990, aboard the Space Shuttle Discovery. The excitement was immense. For the first time, astronomers would have a large telescope above the atmosphere, exactly as Spitzer had dreamed 44 years earlier. And then, the first images came back, and something was clearly wrong. Stars that should have been sharp points of light had halos around them. The images were blurry, not as blurry as a ground-based telescope, but nowhere near the crystalline sharpness that Hubble was supposed to deliver. Within weeks, the problem was diagnosed as spherical aberration in the primary mirror. The public reaction was brutal. Hubble became a punchline. Late-night comedians joked about it. Congress held hearings. NASA's reputation took a serious hit. Here was this $1.5 billion telescope, at the time, the most expensive scientific instrument ever built, and it couldn't see straight. But here's what's really clever about what happened next. Because the error in the mirror was precisely known, it was a very specific, very well-characterized spherical aberration. It could be corrected. Think of it like a pair of eyeglasses. If you know exactly what's wrong with someone's vision, you can grind lenses that compensate perfectly. That's essentially what NASA did, except the eyeglasses had to be installed by astronauts in spacesuits, in orbit, 370 miles above the Earth. The corrective optics package was called COSTAR, Corrective Optics Space Telescope Axial Replacement. It contained small mirrors, each about the size of a coin, precisely figured to introduce the exact opposite spherical aberration, canceling out the flaw in the primary mirror. For the newer wide-field and planetary camera 2, the correction was built directly into the instrument's own optics. The repair mission, STS-61, in December 1993, was one of the most complex and high-stakes shuttle missions ever flown. The crew of Endeavour performed 5 spacewalks over 5 days. They replaced the original wide-field camera with the corrected one, installed COSTAR, replaced the solar arrays, and fixed several other components. The spacewalks were meticulously rehearsed in NASA's underwater training facility because there was essentially no margin for error. If the astronauts couldn't install the corrective optics properly, Hubble would remain crippled, and the entire space telescope concept would have been discredited for a generation. They pulled it off. When the corrected images came back, the difference was staggering. Stars were pinpoints. Galaxies revealed structure that had never been seen before. The pillars of gas in the Eagle Nebula, the deep field images showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length, the precise measurements of distant supernova that led to the discovery that the expansion of the universe is accelerating. All of that came from the repaired Hubble. That last one, by the way, won the Nobel Prize in 2011 for Saul Perlmutter, Brian Schmidt, and Adam Rees. They used Hubble and ground-based telescopes to measure Type 1a supernovae in distant galaxies and found, to everyone's shock, that the universe isn't just expanding, it's speeding up. Something is pushing it apart. We call it dark energy, and we still don't really understand what it is. But the observation that revealed it depended on the kind of precise photometry that only Hubble could deliver. Hubble is still operating as of the mid-2020s, more than 34 years after launch, though it's showing its age. Its gyroscopes have been failing, and there are no more shuttle missions to service it. Eventually, it will stop working, but its scientific legacy is almost impossible to overstate. It fundamentally changed our understanding of the age of the universe, the rate of cosmic expansion, the formation of galaxies, the life cycles of stars, and the existence of supermassive black holes at the centers of most galaxies. And then, of course, there's Hubble's successor. The James Webb Space Telescope, JWST, launched on Christmas Day 2021, after more than 2 decades of development and roughly $10 billion in cost. Where Hubble is primarily a visible light and ultraviolet telescope, Webb is optimized for infrared. And the reason for that is beautifully simple. The most distant objects in the universe, the earliest galaxies, formed just a few 100 million years after the Big Bang, have their light stretched by the expansion of the universe. Light that started as visible or ultraviolet has been redshifted into the infrared by the time it reaches us. To see the very first stars and galaxies, you need an infrared telescope. But infrared is essentially heat radiation, which means the telescope itself has to be extremely cold, or its own thermal glow would drown out the faint signals from the distant universe. Webb orbits at the second Lagrange point, L2, about 1.5 million kilometers from Earth, far beyond the Moon, where a tennis court-sized sunshield keeps the telescope in permanent shadow, cooling its instruments to about 40 kelvins, 40 degrees above absolute zero. The primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's, which gives it about 7 times the collecting area. And here's where Jerry Nelson's segmented mirror concept, the same idea that made Keck possible, shows up again. Webb's mirror is made of 18 hexagonal segments, each about 1.3 meters across, made of beryllium and coated in a thin layer of gold. Gold because it reflects infrared light beautifully. The mirror was too large to fit inside any existing rocket fairing in one piece, so it was designed to fold up for launch and unfold in space. Think about that for a moment. A 6.5-meter mirror, made of 18 separate segments, each of which has to be aligned to within fractions of a wavelength of infrared light, and the whole thing has to unfold itself autonomously 1,000,000 miles from Earth, where no astronaut can reach it if something goes wrong. There were over 300 single-point failure mechanisms in the deployment sequence, 300 things that had to work perfectly, any one of which could have ended the mission. Every single one of them worked. The images from Webb have been extraordinary. Galaxies from when the universe was only a few 100 million years old. Atmospheric spectra of exoplanets showing water vapor and carbon dioxide. The composition of ice in protoplanetary disks where new solar systems are forming. Webb is doing for the infrared universe what Hubble did for the visible, peeling back a curtain we didn't even fully realize was there. And meanwhile, back on the ground, the next generation of telescopes is under construction. The Extremely Large Telescope, yes, that's its actual name, is being built by ESO in the Atacama Desert of Chile. Its primary mirror will be 39.3 meters across, made of 798 hexagonal segments, nearly 40 meters. When it sees first light, expected in the late 2020s, it will have about 16 times the collecting area of a single Keck telescope and will use adaptive optics so sophisticated that it should produce images 16 times sharper than Hubble. The giant Magellan telescope, also in Chile, uses 7 8.4-meter mirrors arranged like a flower to create an effective aperture of about 25 meters. And the 30-meter telescope, planned for Mauna Kea or possibly La Palma, will use 492 segments to build a 30-meter primary. Each of these projects represents decades of engineering, billions of dollars, and the accumulated lessons of every telescope we've talked about tonight. From Galileo's little tube with 2 lenses, to Newton's speculum mirror, to Herschel's giant reflectors, to Hale's great observatories, to the segmented, actively controlled, adaptively corrected giants of today. And that's the thing that strikes me most when you step back and look at this whole story. Every generation of telescope builders stood on the shoulders of the ones who came before, but they also had to solve problems that the previous generation couldn't even have imagined. Galileo couldn't have conceived of chromatic aberration theory. He just knew his images had colored fringes, and he didn't know why. Newton understood the problem but thought it was unsolvable, so he invented a completely different kind of telescope. Herschel pushed mirrors to sizes that were barely manageable with the materials of his day. Hale dreamed bigger than anyone thought reasonable, and then made it real. Twice. The CCD inventors at Bell Labs were trying to build a better computer memory and accidentally revolutionized astronomy. Jerry Nelson sketched segmented mirrors on a napkin when everyone said it couldn't work. And right now, somewhere, an engineer or a physicist or a graduate student is working on the next idea that will seem obvious in hindsight, but seems impossible today. That's what 400 years of telescope engineering really is. It's a conversation across generations. Each generation asks the universe a question, builds the best instrument they can to hear the answer, and then passes what they've learned to the next group, who ask a deeper question. The instruments get larger, more precise, more sensitive, but the impulse behind them is exactly the same one that made Galileo point a tube with two lenses at Jupiter in January of 1610. It's the same impulse that made someone, thousands of years before that, look up at the night sky and wonder what those lights were. So as you lie here tonight, maybe drifting off, maybe still listening, think about this. The light from distant stars has been traveling for years, centuries, millions of years to reach us. And we've spent the last 4 centuries building increasingly ingenious machines to catch that light, to bend it, focus it, split it into its colors, record it, and decode the messages hidden inside it. Every photon that lands on a telescope mirror has a story, where it came from, what it passed through, how old it is. And the telescope is just a patient listener, gathering those photons one by one, building up a picture of a universe that is far stranger, far older, and far more beautiful than anyone could have guessed when a Dutch spectacle maker first noticed that 2 lenses held at the right distance made the church steeple look closer. That's a good thought to fall asleep to, I think. The universe has been sending us letters of light for billions of years, and we've only just learned how to read them. Good night.